Ecologists spend a lot of time examining populations, which are a group of one type of organism that lives in one area. And they do this because they want to be able to track how these populations interact with the members of their own population and also with other species. And they can track and see how things are changing and make predictions about the kinds of things that might happen in the future. So what kinds of things can affect the size of a population or how big it gets? And of course, one of the things is going to be number of births. Sometimes we call this natalities. And then the opposite of that, which is the number of deaths, which are fatalities. There's also sometimes organisms that may move from one population into a different population, which is immigration. Or if individuals leave that population and go somewhere else, that is emigration. That's going to remove individuals from the population. So, and this seems kind of, self-evident here that birth and immigration will add individuals' population and death and emigration will remove individuals from the population. So we can calculate changes in population size by focusing on the births minus the deaths and the immigrants and minus the emigrants. Now, why, you might ask, would organisms immigrate or emigrate out of their population? Sometimes we think of human populations, we can do that, but say, for instance, we're talking about some deer. Why would the deer that live in this area of Illinois leave or maybe even come here from other areas? And that would be maybe a lot of times it has to do with things like shortage of food or shortage of mates or even just looking to go find mates in other areas. Exponential growth occurs when individuals reproduce at a constant rate. In other words, a lot of times they're kind of reaching their full biotic potential. And it's easiest to think about exponential growth when we think about any sort of population that may start off a little bit slow, starts off small, and it starts increasing every generation. But the larger the population gets, the faster it's going to grow. And if you look at a graph of this, you're going to see something that looks like this graph here. So we may have something like just a couple of deer here in the beginning, and then by the time as time goes on, the number of deer just really increases quite dramatically. I think a good example, easy way to think about this is bacteria. So let's say, we've got some bacteria, and, one bacteria just splits in half, makes two bacteria. And if we just started with one bacteria, after 20 minutes, we'd have two, and then after 20 more minutes, we'd have four, and after 20 more minutes, we'd have eight. And if it did this for 24 hours, how many bacteria we would have? This is our number. I think this is something like 4 sextillion, 720 quintillion. Not even sure if that's the right number, but that's a crazy amount of bacteria. And bacteria would really sort of be able to very easily take off the world if they continued to grow like that and always grew like that. So we know that exponential growth can't go on forever for any population, just because there's just not enough space here on Earth for that many living things to be here if we all just sort of kept going through exponential growth forever. So what types of things affect whether or not exponential growth happens and how much exponential growth happens? Well, it's going to be things like the age at which an organism first reproduces. Some of animals that we know, like bunnies and mice, can actually reproduce after they haven't been around for that long. And so that's one of the reasons why it's so easy for those populations to get bigger fast. Also, how often does reproduction happen? The average number of offspring produced each time. So humans, on average, we really only have about one person every time we reproduce. But there are many organisms that may have hundreds of babies every time they reproduce. The length of time it takes to reproduce, elephants, it takes them closer to 2 years to give birth to a baby. And so we know that their growth rate or their ability to undergo exponential growth is a little bit different even from us, and definitely different from things like mice. And then finally, the death rate of individuals. So if we look back, some of those, insects and stuff that may have thousands of babies every time they reproduce, so many of them die that's why their populations don't keep growing exponentially forever. Even so, here's just kind of one example here where you can see that two different populations. In the line in red here shows a population in which the reproduction begins at just 4 years of age. And then the second graph shows a population in which reproduction begins at 6 years. And so you can see that the later in life that a population starts reproducing, sort of the slower exponential growth they're going to experience. Or on the other hand here, population of bacteria, you can see that the higher the death rate, the slower the exponential rate is going to be. So that line in red shows a population in which those bacteria aren't experiencing death, and you can see how very quickly their population sort of escalates and gets very large. All right, so what stops populations from growing exponentially? It has to do with a lot of things that we kind of call environmental resistance. Usually populations can't just keep getting bigger and bigger and bigger forever because they're going to run out of food, especially like you think about that bacteria example. My guess is they'd run out of food rather quickly, or they run out of space, or something comes along and eats them, like any sort of predator there. And there's even disease. So there's many, many things that keep populations from growing exponentially forever. All populations we know that go through exponential growth must eventually stabilize or slow down their growth, or you may see some sort of crash. The one exception to this so far has been the human population. This is a graph of the human population growth, and you can see that early on in this graph, our population grew very, very, very slowly. So there wasn't really a lot of growth here in the beginning. And more recently, we have been growing like crazy. And this graph shows that we're at 6 billion. And actually, because this graph stops at 2000, we are over 7 billion people already. And so you can see that we're definitely going through crazy exponential growth. Now, remember, I just said all populations must either stabilize or crash. And there's a lot of scientists who are very, very worried about this and hoping that we can find a way to stabilize our human population before we see a crash. Some organisms kind of periodically go through these cycles where they go through really rapid exponential growth and then there is a crash. So we see this often in rapidly reproducing species like bacteria and insects, where kind of all of a sudden they explode like crazy, then they run out of food, and we call this sort of a bust, where their population kind of goes down in size and remains small again for a while. Let's talk about logistic growth, which is a little bit more realistic pattern of growth. And when a population's growth either stabilizes, kind of slows down, stops after some sort of period of exponential growth. And when that logistic growth is hit, it's when the birth rate kind of equals the death rate, immigration is equal to emigration. There's just really not a lot of growth happening in that population anymore. So I like this kind of graph because it shows us in red is sort of our original type of growth that we were talking about, where population just keeps getting bigger and bigger. And that blue line is going to show us a little bit more realistically what happens when we have logistic growth. So we kind of get this leveling off of the population. Logistic growth, and we had to talk about kind of a good definition here. It's when populations just kind of keep increasing until they hit some sort of number, which is sort of the maximum number sustainable by their environment. And if you've ever been in an elevator and you see maximum capacity and it's got a weight and it's been overcrowded and you start looking around and getting nervous because you're worried that we're over the maximum capacity. And most populations have some sort of maximum capacity that, any given area can only sustain a certain number. We could not have 3 billion deer in Palos Park. They just wouldn't fit. I'm sure there is a maximum number of deer that can really just sort of realistically live healthy, happy lives in Palos. Now, logistic growth doesn't mean that the population hits that maximum number. So let's say the number of deer that can live in Palos is 10,000. That even seems a little high there, but say that's the number and it hits 10,000. It's not going to ever be able to stay exactly at 10,000. There's always going to be sort of a lot of ups and downs until we kind of hit an average population size. And that number that the population seems to kind of go a little bit above, a little bit below, up and down around is called the carrying capacity. So instead of calling it the maximum capacity, we call it the carrying capacity. And that's really just that maximum number of organisms that can be found in one area without really damaging that ecosystem. So let's take a look at this graph of the sheep. And I like the orange line a little bit better because that's a little bit more realistic. And you can see that this population of sheep in the beginning kind of started off with some exponential growth. And, they kind of grew up rapid here. And then you notice they sort of got a little bit too high, a little bit more than that area could really hold. Looks like at about, 1.8 million sheep. And once that might have been, there wasn't enough food or enough space for that many sheep to live in the area. And so you see the population, some of them will die off because they're just going to starve and not have enough food. But then it kind of goes down here, maybe about 1.4 million sheep. and suddenly there is more than enough food for the sheep that are there. And so it's a happy day for the sheep, and they kind of go up, and then maybe they get to about, I don't know, 1.65 million sheep. And that's a little bit more than they can hold. And so some of them die off, and then there's more food. And so it starts going up, and then a few of them die off, and they come up. And it kind of goes up and down and up and down and up and down. And so if you were to ask me what's the carrying capacity of sheep in this area, I would take sort of the average between all those ups and downs and say maybe about 1.55, 1.6 million sheep. That seems to be the approximate carrying capacity. We know it's never going to be this top number here, because if it was the top number right here, then definitely we wouldn't have had a reason for the sheep to die off. Let's take a look at this graph of barnacles. What do you think is the carrying capacity of barnacles in the area? Remember, it's never going to be the top number, because otherwise we wouldn't see this sort of period of death. So I would go for something that's kind of in the middle of the ups and downs. Oops. And that would probably be, what do you say here, about 75 barnacles per cubic centimeter. And if you look, you can see once again, just for any sort of population, there's never, the red line is sort of the idealistic line, and the black dots are going to show the, what the actual numbers of population might be. Now, there are some consequences for populations when they go over the carrying capacity. The hope always is this, is that the population will go through exponential growth kind of slow enough, as you can see on this green line here, that it may go a little bit over their carrying capacity, but then you'll see a little bit of a die-off, and then you'll see a little bit of an increase in population, and a little bit of a die-off, and you'll kind of see this sort of happy leveling up and down in the population. But sometimes populations, as shown in the red, will grow so fast, so quickly, that they'll go really, really, really far past the carrying capacity, and they'll create really a crisis for that population. Because there's so many all at once, almost none of them may get enough food. And so you'll see almost all of the organisms in that area die off. And this can be quite devastating for populations. Sometimes they can be completely destroyed if they actually grow too fast, too quickly. Now, sometimes populations grow too fast, but maybe not quite as bad. And most of them will die off, but enough will survive that maybe eventually you can see them start to kick back up. But sometimes then maybe not, it may not recover to the same size that it was able to hit initially.